Okay, so what we are going to see today, first of all, is the concept of sets. So what is a set? You already know what is a set. A set from maths, from the theory of mathematics, you know the set theory. It is, a set is basically a collection of unique items, right? Let's say if A is a set of 1, 2, 3, and let's say B is another set of some other items, let's say 1, 3, 5. Then both these are a collection of unique items. And you have studied in the set theory, there are different operations which are possible. Let's say union operation, right? Which means A union B. What is that? Yes?
1, 2, 3, 5.
1, 2, 3, 5. Very good. And then there is something called intersection. What is this? A intersection
1,
B is
3.
1 and 3. That's it. These two are common operations. And then you can define other operations, let's say difference operation. But anyways, I will not define so many, means maybe a few useful ones are sufficient. Now, you can define a data structure which carries these collections and which has these functions defined on them, right? Let's say you define a class called set, and you will initialize this class by saying what are the entries here. Let's say you want to define class variables, self dot maybe just an array, and you can initialize it with something, and then you will say define union of self comma. So you are defining union of this set with another set, right? Let's say some other set S, and you can define the union, which basically returns another set, maybe some union set US, let's say. And then you can define intersection of this self with some other set, let's say S. And then this will also return some intersection with S, something. Okay. So this is how you can define your class. Nobody stops you from doing it. Another useful operation is if you want to add new elements to the set, right? Let's say add, which basically adds an element. Let's say if I give add an element add an element A to the set. So basically this will return. So let's say if my original set S was equal to B, C, D, and then this function will return A, B, C, D. They could be ordered or not, doesn't matter. It's just a collection, not an ordered collection. And let's say if my S were already A, B, C, D, or let's say if now let's say if I use this set and I again do this set dot add A, then this will return the same ABCD. A will not be repeated, it will stay the same, right? So in this way, you can define these operations in your class. I think this is a very simple abstract data type, and a very good implementation of sets in Python is already existing, which you can directly also use, no problem, in Python. And say my A is a set, let's say 1, 2, 3. And so this is how you define set with curly braces. Curly braces or set, right? If you define it like square brackets, then that will mean a list. If you define round brackets, that means a tuple. A tuple cannot be modified. Means a tuple is a fixed data type. So, sorry, it does not modify, unmodifiable. Whereas list can be appended or removed. Some elements can be removed from there. Set can also be appended, etc. So let's say I have a set B. B is 1, 5, 1, 3, 5. And there are inbuilt functions in Python, A dot union B. This will return A union B basically. So in this way, you can make use of it if you want. Okay, that was all about sets. I will, yeah, okay, I think I can stop here. Now I will go back to our problem where we left last time. This was a practice problem on graphs. And the problem said, do I have it? Okay, I have it here. Yeah, the problem was to clone or to copy a graph. I have a graph which is defined like this. Define node. No, node is a class, I'm sorry. Node is a class, right? And what does it contain? Define, init, etc. I'm not writing the full thing. It just has some value. Maybe you can pass it here. Self comma v, some value, and self dot neighbors. This is a list. Okay, that's it. These two things are there in my node. Yeah. This is the class node. Now using this node, I can define a graph. I can define a graph. And the task is, given a graph, I want to find the, I want to make a copy of that graph. Let's say this was a graph 1, 2, 3. This is the graph, right? And if I give you any node of this graph, let's say if I give 2 as an input. So let's say I'm going to define some copy. And I give as input any node, which is an instance of this node class. That's it. And you have to return another node, which basically is the same graph. Means if I modify this graph is not affected, right? Because I can simply say return node. That will also do the job, right? It is returning a copy, but this is actually not a copy. This because this points to the same graph. Let's say if this node was this node, then when you say this return this node, it will also return this reference to this node. So basically inside your memory, say this is your memory, then the same thing will be returned. So if you modify this returned thing, original thing will also be destroyed, right? So that's not what you want. Rather you want to return, you want to make a new graph here, which is a different graph. It's same graph, but stored in a different memory location. And this node should point to now this node. So that even if I modify this graph is not affected, right? Okay, so tell me, how can you do this? Did you think about it?
Sir, we can traverse the graph and copy the content of each node into creating another node.
Yes, very good. So we have to traverse the whole graph, and then we have to, as we are traversing, we have to create this new graph. Okay, let's see if we can define our function copy. Yeah, how do I define my function? Okay, I want to traverse it. Okay, how will I traverse the graph? I can use either recursion or a what is it called? A queue, right? DFS or BFS. Which one is easier to write?
Using stack recursion.
Yeah, we can use sets, but okay. How will you do it? So first of all, let's talk about graph traversal. How will you do graph traversal? There are two methods possible, either DFS or BFS. What is DFS? Depth first search.
We will go to each node and then we will traverse all the neighbors, and on all the neighbors we will call this DFS, and also we'll keep track of the nodes we have visited till now.
Okay. Yeah. So yes, you have to keep track of all the nodes also. So let's say there is some memory. Right. Memory is a list of all the nodes which have been visited, or it could be a set also, right? Now this memory could be a list or a set. Okay, now what we will do is, first of all, I will process this node, right? Let's do pre-order search or pre-order traversal. So I will process this node. It could be printing or whatever. Process this node, and then put this node in memory, right? Right? But we have first to check whether this node is already there in memory or not. Right? It could be already a traverse node. So you can put a check here if node in memory, then return, right? And then you will append the node in the memory, and then you will basically for n in node.neighbors. Node.neighbors is a list. You will pick every element of the list, right? And you will traverse. Let's say here, let's say you're here, the neighbors are 2 and 3 in the list. We'll first do the 2 and then 3. So what will you do here? You will process n, right? And that's it. Then you return. Okay, whatever it is. So this is how the DFS works, right? Let's this is just for a recap. Now come to the problem. What we are going to do here? If we do a DFS on this graph, how shall we create this new graph? So first thing you have to think about is, where are you going to store your new graph? There are two ways possible. One way is that you are returning the new graph, right? The other way is that you maintain a global variable called a graph, and you are appending or manipulating that global variable. There are two ways, right? Anybody knows of any other way? I can create a global variable here called copy graph, or copy or graph, or let's say node to or graph to something. sorry, graph underscore copy something. And I can, in this function, I can just again and again write to this graph copy. This is one way. Other way is that this function returns the graph copy, right? Return the copy, graph copy or node copy, whatever. Right? Both the ways are possible. Let's start with, let's say I want to return because, okay, let's start with the first method. Okay, let's return the graph. So basically this function will return a node which is copy node or node copy, right? How shall we do that? And as you know, if you're doing a DFS, then you have to also keep track of memory. Okay, let's add the memory also here. Okay, so what shall I do first? I'm at the node N, so this node, this node. I have to create this node now. I'm standing here. This is my node is pointing to here, right? My node, this node points to here. What shall I do now?
Declare a new node with node.val and node.neighbor.
Yes, I declare a new node. Let me call it as a copy node, or C node is equal to a new node, right? An instance of the node class, and the value at this node will be same as node.value, right?
Yeah.
Okay, now I have created this node with the value 2. Now what will I do?
Now C node.neighbors equals self.
Yeah, I have to, okay, let us put a loop, right? For n in node.neighbors, C node dot neighbors is equal to, or dot append, what shall I append here? What do I have to append? So n is this, n is this, huh?
Okay.
A new node, sir.
A new node, yes, n dot value, right? So I have created a new node. So okay, I was here, I created this one. Now I created a name, this node with the value 1, reading from here. Yes, now what next?
So one question, if we do this, then we will create node 1 from both 2 and 3.
Yes, good point. Very good point. If you do this, then what will happen when you go to, okay, you can, then again, you will go to the second iteration of this loop. You will create a 3, right? This is also created. And then, I don't know how you are planning the further progress, but when you go to 3, let's say you are here now, then you will again create a neighbor called 1 and a neighbor called 2. So how will you know that this 2 was actually this 2 and this 1 was actually this 1? So that you're not tracking, right?
So, sir, we are not copying the neighbor.
We're not copying the neighbor means?
Self.neighbors is also something like we have to copy it also, like C node.neighbors equal node.neighbors.
C node.neighbors equal to node.neighbors. Yeah, that's what I'm doing here. N is the node.neighbors, no? Oh, if you copy the list, then the neighbors will become this, right? The neighbors will point to these. We don't want that. We want to create new neighbors, right?
Sir, can we do this? We go to the neighbor first, and when we are returning, then only we assign the neighbors, so that all the neighbors are created, and then only we fill the neighbors list.
Yes, yes, very good, very good. So instead of creating new thing, you just recursively call this function, right? You use this function to create new nodes and recursively call it. Does it make sense? No? Did you get the problem? What is the problem here?
Yes, sir.
Okay. The solution is something like this. Solution is that when you are at 3, how will you know? You know that this when you are here, you have created this one, and you know the neighbor is 1, but you don't know whether this neighbor is already created or not, right? If this is created, then you just link this one. If this is not created, then you have to link, or you have to create a new neighbor, right? So what we will do here is, we will add a step here. If, okay, so this return will be, it returns the C node, right? The copied node. This function returns the C node. Now, but here, if my node is already there in memory, let's say if you are at 3 and if you were at 3 and the neighbor was 1, but this was already there in the memory. This means there is some corresponding new node also, it must be there already created. So we create a map from the old node to the new node. We have a map which stores all these mappings. This map from old references to the new copies, they are there in this memory. So basically, instead of calling it memory, I will call it a map. So you check if your node is present in map, right? Let's say here, my map is mapping from 1 to this one, old one to new one. If my old one is already there, then I can return the new one, right? Then return map of node, right? Given this old thing, if it's already there in the map, then return the new value. And if it is not there, then you create a new node, right? Then let's say if it was not there, then you created a new node, and then you iterated over all the neighbors. But here also, same thing will be recursed, right? Instead of saying this, you will say, copy graph of n, right? So that you can recursively traverse the whole graph. This was our DFS, right? Inside this neighbors, you have to process the node n. Basically the same, oh no, it's not process, it's DFS. Nobody pointed out this error, right? DFS of n. That's what you're doing, the DFS of n. That's how you do it in the stack, the recursive stack. All right.
Sir, what is map? A new list or what?
The map is the mapping from old nodes to the copied nodes, the new nodes. Because when you are traversing, you're traversing only the old nodes. And as soon as you hit a new node, you can either create a new node, or if that node is already present in your map, then you can just this means it has already been created. Why to create it again?
Sir, what kind of data type is map?
Map.
Sir.
Map is a, okay, good point. Did we not discuss this? Okay. Map is a map. Oh, how do I say? It's a, okay, what is the map? Map is basically a map from one kind of elements to the other kind of elements, right? And it's a function. It's a function over discrete objects to discrete objects, right? It's a function from some discrete set S to some other discrete set S dash. Okay, so
Sir, can we use dictionary?
yes. So Python has the implementation of map as a dict. Python has dict. So, okay, in dict they use square brackets. Here you have to add, okay. To add a new value, you just say map of node equals node. You can do it either here or you can do it later also. Sorry. Sorry. Is that clear?
Sir, can you summarize this algorithm once more?
Good. Okay, I'll do it. The task is to copy the data from old graph to the new graph. So we will be traversing the old graph, and as we are going, we will construct the new graph. But you know that the graph is, there is no one direction of traveling. It can travel in any direction. So starting from this node, there is no fixed rule that you should go to 3 and then 1, as you had in tree. Like tree was simple, right? You are only traversing downwards, starting from the root. But here there is no fixed rule, so you can traverse in any direction. You can go from 2 to 1 to 3, or 2 to 3 to 1, or you can start from 3, go to 2 and 1, etc. So therefore, you have to maintain some memory that what nodes you have already traversed. But in this case, just maintaining a memory of nodes is not sufficient, because each node corresponds to a new node, a new copied node. That's why you are also maintaining a map from the old node to the new node. This map will be used when you are making the linkages. When you visit a new node, when you create a new node, you have to link it with one. And this node was already visited before. Since it was visited before, this means that there must be a corresponding copy which must be there. So that copy is stored in the map. So map stores the previously visited node as well as the corresponding copy. Now you link 3 with that corresponding copy, because you cannot link 3 with the old node. You have to link it with the new node only. So therefore your map should contain both the informations, old node as well as the new node. Okay. So this is the kind of thing. We have done simply a depth first search, a DFS traversal we have applied, but just with the help of this map, we are making the linkages, the neighborhoods are defined. Okay.
Okay, sir.
Good. Yeah. Map. Let me see if I can speak a little about this data type called a map, or basically a table from one kind of discrete elements to the other kind of discrete elements. It seems I don't have it. Here, a map is essentially, the requirement is that these should be unique keys, right? And this can be any data. This need not be unique. Yeah. For example, you have a map from some name, maybe Hari. This map of Hari, I take a key from here, maps to, let's say, 5. I can say map of Kamal maps to 5. So this target domain, the domain may not be unique, but the our domain has to be unique. The range may not be unique, right? So this has to be unique, whereas this may be repetition. Now I cannot again have map Hari equal to 6. Now this will overwrite. A unique keys have to be unique, and the values may be overlapping. Key and value. So basically, map is a pair of key value. Map is basically a key value pair. And when you give a new key, it will quickly search for this key in all the keys, and then the corresponding value it will retrieve. Right? So let's say you have a set of all the numbers, could be a list or whatever. How you implement this abstract data type doesn't matter. Means the complexity will be different, but just taking some names. Let's say these are my keys. Now my values will be this. Kamal will map to some value. It could be a value. It could be a matrix. It could be another data type. Doesn't matter. Anything can be here. And Hari will map to something. Ram will map to something. Sita will map to something. Right? But just that my keys have to be unique, and the keys should be unmodifiable, not modifiable. Which means I cannot map a list to something. Let's say my key cannot be a list. Cannot be a list or anything modifiable. It must be unmodifiable. Right? Keys must be unmodifiable. You can, so it cannot be a list, but list is not allowed, but tuple is allowed, because tuples are not modifiable. You cannot add new elements to an existing tuple. You have to define a new tuple, whereas a list is a dynamic array where you can add new entries and you can modify. Tuple is a constant thing. Once you created it, you cannot change it. You have to create a new one if you want to do it, anything to it. Similarly, strings are also not modifiable. So they can be used as keys. Because once you create a string, you cannot modify it. Whenever you try to modify it, you basically create new strings. For example, you are saying my some string str is equal to Kamal, and you want to, let's say, you want to create a new string too, which is str plus, let's say, Hari, Kamal Hari. But this will create a new string. It will not modify the original string, right? So in your memory, somewhere Kamal is there, somewhere Hari is there. And this operation will not modify any of these, rather it will create a new string called Kamal Hari. Okay. So that's the thing. So you can only put here, the keys can be only undestructible or unmodifiable entries, whereas it makes sense, right? For example, if I modify Kamal Hari, if I modify one of these entries, then the whole mapping will change, means that is not allowed. Okay, so the reason why we cannot have changeable things is little more complicated. The reason is this: generally, if I ask you, can you search in the list of keys, can you quickly search Hari? So what you have to do, you have to do a linear search. It will take the complexities of the order of n. But what this mapping does, it converts this into a more efficient form where the search is very fast. So if as soon as you put here map Hari, it will basically, this Hari will be quickly searched in this new data structure. And that data structure has a very fast search. That's why the keys, they don't allow modifiable keys, because otherwise that whole data structure will change, and that will be a very costly operation, right? Because the only operation you need in the map is to search for this key and then return the corresponding value. That's it. So that keys have to be arranged in a data structure in a way that they're very easy to search. That's why they don't allow modifiable. So I can add a comment here for data structure is optimized for quick search of key. Therefore, we don't allow modifiable keys. Okay, is that all right?
Sir, what type of algorithm does it use to search for keys?
There are algorithms which are a little complicated. Okay, generally what is done is that this will be converted into a number. So every key will be converted, let's say, into a number or a binary code. And then those numbers can be stored in a data structure when then they are searched for, right? Because my key could be very long. Let's say this is a whole long text of maybe 100 characters or 500 characters. So what is done in the algorithm is that whole thing is compressed into a very short representation. Let's say here the representation could be simply 0, 1, or 0, 0, 0, 1, 1, 0, 1, 1. And immediately when you see 0, 0, you can immediately find out, okay, this is my key. Search is very fast.
But sir, now if I add one more key,
Yeah,
it cannot be represented by 2 bits. So all key mapping needs to be changed, right?
yeah, yes. So generally this is a little long, and this is a little long representations. And yeah, yeah. What internally can be used is a tree kind of structure, right?
Yes.
Okay. So any more questions here? Okay, I think, yeah, that was the new thing, that this mapping, I think it's a new topic which I didn't cover before. Can you do this problem using BFS now? The same problem, instead of using DFS, can you do it using BFS? That's the homework for you. Okay, do it using depth first search. Okay, now I'm going to discuss our next topic, which is I will discuss now dynamic programming. I think I can look dynamic programming. Anybody has any questions until now?
Sir, one thing is dict in Python immutable or mutable object, or dictionaries in Python immutable or mutable?
Dicts are mutable, but their keys are immutable.
Keys must be okay. Okay, sir. So if once a dict is created, we can change the keys, or we can add more keys and values.
Yes, you can add more keys. Yes, that's what we are doing here. We are adding more keys
Okay.
and more values correspondingly.
And can we change the key corresponding to a value? So if suppose Kamal and 5 are a key value pair, and can I change just Kamal to something else?
You can create a new key, map it to that value, and then delete the old key. Means like basically the value has to be created again. Like create a new key. Yeah, basically you can map to the same value if it's called by value. Sorry, call by reference. Yes.
Okay, sir.
So basically you will say, let's say I want to make Kamal to Kamal 2 or something. I will say map Kamal 2 is equal to map of Kamal.
Okay.
This will return 5 and it will assign it to this one. Right? Now both have value 5. Now you can say delete map of Kamal.
Okay.
No, I forgot the syntax for deletion in the in this. I forgot the syntax. Maybe you can check.
Okay.
Okay.
Thank you, sir.
Thank you. Okay. Now I'm going to the next topic, which is called dynamic programming. So what is dynamic programming? In short, dynamic programming is called optimization in recursion. Before I give the definition, or before I explain the definition, let me give you an example. All of you know what are Fibonacci numbers? What are they? You start with 0 and 1. Then next number is?
Adding previous two elements.
Yeah, 1 plus 0 is 1. So 1. Then 1 plus 1 is 2.
3, 5, 8, so on.
Yeah. So these are Fibonacci numbers. If I ask you, can you return nth Fibonacci number? Nth Fibonacci number is, let's say 0, 1. This is the 1, 2, 3, 4. No, okay, let me go to 0, 1, This is the index. These are the indices. Like these are the indices. Okay, starts from 0 and then goes on like this. If I ask you define Fibonacci number, nth Fibonacci number, how will you return? So you can say this is one algorithm. Pardon?
We can use either for loop or recursion.
Yeah, let's use recursion. I want to use recursion, then what will I do?
If n is 0 or 1,
Okay, if n is 0 or 1,
if n is 0, return 0. Else if n is 1,
sorry,
then
return 1.
return 1.
Okay,
Else we will call fib of
we'll call
n minus 1.
okay, return
Fib of n minus 1.
n minus 1
Plus n minus 2.
right? That's it. So what is the complexity of this algorithm? Order
N.
Order n. Are you sure? Are you sure it's order n? Let's start with n equal to 5, let's say. For n equal to 5, what will it do? It will first, so I'm running fib of 5. This will call fib of 4 and fib of
3.
3. Now fib of 4 will call fib of 3 and fib of 2, right? And this fib of 3 will call fib of 2 and fib of 1. And this fib of 3 will separately call fib of 2 and fib of 1, right? And this fib of 2 will separately call fib of 1 and fib of 0. It keeps on going, you see. This fib of 2 will again call fib of 1 and fib of 0. Yeah, and these fib of 1, fib of 1, fib of 1, 0, they won't call anything because they are just returning a number. So what is how many function calls are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18, right? So it's exponential actually. What will be the general formula? Will it be 2 to the power n? Something of that sort.
Yes, sir.
Okay. Can you prove it? Can you prove it? It's 2 to the power n.
Sir, each function will call two other functions, and then each of those two functions will call two another functions. So it will be like recurring twice, getting twice each time.
Yeah. Yeah. Yes. Yeah. So it basically it's forming a complicated tree, which is okay. So this is very inefficient, right? This complexity, exponential complexity, is very bad. can we make it a little more efficient?
Sir, we are calling like fib of 4, fib of 4.
Yeah,
So if you can optimize that, then we'll do.
yeah. We are calling same thing multiple times. Rather, if we just save the values somewhere, right? If I make a map from 4 to the actual value fib of 4, then that map can be reused again and again, right? So that is called dynamic programming. That instead of calling the function again and again, you save the values and in a cache or in an array or in a map, where later you can retrieve the values without going into the loops again.
So, sir, won't it increase the memory complexity?
Memory constraints, yeah, but how much memory will be required? Okay, what will be the complexity of that algorithm, the runtime, the time complexity? Let's write an algorithm first for Fibonacci using dynamic programming. So what we do is, okay, we define an array, which is the memory, which is the holder. Let's call it as f. F is a map. Say f of 0 is equal to, what was f0? 0 was 0, 1 was 1. Okay, now this map I can use to compute. How will you do it? Now you can put a for loop here. For some m in range, you will start from 2 and you will end at less than n plus 1. Right? Then you will say here f of m is equal to f of m minus 1 plus f of m minus 2. Right? And then when this is done, then you will just return f of n. Okay. What is the complexity, time complexity? Time complexity is? Yes?
Order in.
Order n. And space complexity is?
We'll be storing in values, so it will be.
Yeah, n. But you mind it here, the space complexity. What was the space complexity here? Where is the space being consumed in this algorithm?
In the stack, I think.
Yeah, in the stack. Yeah. I don't know how much will be the space complexity, but maybe very large. Looks like of the order
It will
of.
also be exponential, I guess.
Might also.
Pardon?
Will it be exponential?
Yeah.
Like,
Yeah, I don't know exactly. Maybe you can compute. Yeah, should be. Yeah, should be. Yeah, could be exponential. It could be exponential. Yeah, of that order. Yeah, probably. I didn't verify it, but yeah, you can verify.
So,
Okay.
sir, in the stack, each time if like F4 is called, then F4 will call F3 and 2. So each recursion will keep on stacking two functions. So it should be 2 to the power n.
Yeah, yeah.
Like that.
Yeah, yes. I agree with your logic. Yeah. Okay, so and see, this is very efficient, right? It is using less memory, less time. So this is dynamic programming where you use some memory to make your problem simpler. So
yeah, sir. In that algorithm,
yes,
We are signing like f1 equals m minus 1 and f m minus 2, but those two are not defined, right? Okay. Oh, yeah, got it. In blue. Okay, fine.
Okay, so here in DP, what you are doing is you are optimizing the recursion by storing the results of sub-problems, right? Here, this was a sub-problem, and -1 is a sub-problem, and -2 is a sub-problem. And you are storing those results in an array or a map, right? Or dict. So basically, what is the benefit? The benefit is your time complexity reduces. Time complexity goes from exponential to linear. Even space complexity, but okay, anyways, time complexity is going from exponential to linear. Okay. Yeah, so that's it. Now I will give one problem which is fairly straightforward, and it will be using the concept of dynamic programming. Let me open this problem and I'll give it to you. Okay.
Sir, in dynamic programming, using mapping is the only way to do solve the problem, or there are other ways in which the problem can be solved?
Generally, you maintain an array or a map or a dict to store the values.
Okay, sir.
Like here, we are maintaining capital F to store the answers of the sub-problems. Right? Recursion basically breaks your problem into sub-problems, right? And in dynamic programming, you are using the map to store those answers. Okay, this problem is like this. This is a sample problem. I should have written an example. Okay, so I have a matrix. And it has numbers written. I am just writing randomly. Some numbers. You have to start anywhere from this boundary. Start anywhere from this boundary and end anywhere at this boundary. And pick up a path. You can go either in this direction, or this direction, or this direction. Basically, you can make local moves which are either left to right, left to top right, left to bottom right. These three moves are possible. You have to start anywhere here and end here while gathering maximum points. That is the goal. Find the path. Path that gathers maximum point. Have you seen this problem before? Have you seen this problem before?
I've seen similar problems, sir.
Yeah, where?
Like in physical design, we have to go to uh, automating it with see such type of algorithm. Like we have to path from one point to other point in like assigning the route path.
Hmm. Yeah. Yeah. Anybody else? No. Okay. How many of you here are from communication stream? In communication, you see something called bit-to-bit algorithm.
Yes, sir.
Yeah. So that is something similar, right?
Yes, sir.
Okay. So let's first write down the solution in a recursive way. So define this is the recursive solution. How will you do the recursive way?
So like for any element, choose the maximum of its possible elements, and then on that maximum element, call the function again.
Yeah, yes. So whatever is the value here, let's say I will call it as the score. Okay, score is fine. Score at some point, let me call it as I comma j is equal to the basically the value at I comma j, which is 5. Let's say means whatever is the basically this is value at I comma j. Let's say this matrix is called A. Let's say then A of I comma j, right? Let's say it's a numpy matrix, right? A of I comma j plus, yes, who will tell? Yes,
Score I plus 1 comma j plus 1.
score I, no, plus 1, minus 1, could be minus 1. I minus 1, comma,
J minus 1.
j minus 1.
So j minus max of j minus 1 and j minus 2.
Okay, max of score I minus 1, j minus 1,
And the score of
comma,
I minus 1, j minus 2.
are you sure?
J. I
Let-
minus 1 and j.
I minus 1 and j. And
J plus 1 also. Like a score of I minus 1, j plus 1.
yes, I minus 1, j plus 1. Because my, if I'm reaching here, let's say, I can reach from either I minus 1 comma j or I minus 1 comma j minus 1 or I minus 1 comma j plus 1. Right? 3 nodes I can come from. Right? So this is how it is. So one thing is clear, I have to maintain, okay, no. So how will you solve it using recursion first? Fine. Accumulated score, or fine, just say score. So now define okay, let's first try to find the maximum score only without saving the path. Path saving can be done, but let's first focus only on calculating the value. Define score at the point I comma j, right? I comma j. Okay. How will you write it? You will say this is my ai comma j. Okay, first of all, you may, okay, let me write directly. ai comma j let's say some s is equal to plus maximum of, actually the same form can be written here, right? I comma j, or I minus 1 comma j minus 1. Same can be written here, right? This is a recursive form. Okay, then where is the terminating condition? Where is the terminating condition?
When I equals 0.
Yeah. If I equals, no, I can be 0. I cannot be less than 0. Right? If I is less than 0, or j is less than 0, or I is greater than whatever is this maximum value, right? I is greater than equal to a dot shape 0, or j is greater than equal to a dot shape 1. Then you return 0. No, return, yeah, return 0, right? That's it. All right. When any of these conditions is met, then the score is 0 in these places.
Sir,
Yeah.
sir, suppose when we have j as the maximum value, like ij, that bottom corner, bottom right, the value 5.
Yeah.
So when we are evaluating this s is equal to aij plus max of that statement,
Yes.
then j score of I minus 1 comma j plus 1 is not there.
Yeah. So it will return 0, no?
So but we are just checking for j, not j plus 1.
No, see, when you are calling this function, when this function is called, it is called as j plus 1. But once it reaches here, then this
Yes, sir.
variable j will be equal to that new value 6 or
Yes,
5.
sir.
5. Yeah, so be careful of these things because the variables are local to a function, right? This I and j are local to this function. When I call a new function, then in the new function, the I and j will be different, right? So in the stack, you are storing not just the location of your code, but also the values of local variables, right? Right? And then you create the stack. You're storing, when you hit this statement, you have to compute score I minus 1 comma j minus 1. So you'll put everything on stack here, the value of I, value of j, etc. Then you call the function with these new values. Then now I and j are updated here. Okay.
So what is shape? A dot shape 0, A dot shape 1.
Acha, this I'm using the convention of NumPy. NumPy uses A is a NumPy matrix, and A dot shape 0 basically means A dot shape is actually an array 5 cross 5.
Okay, okay.
So A dot shape will be 5. Sorry, A dot shape 0 is 5. A dot shape 1 is 5. Basically,
Okay.
A dot shape. Sorry, A dot shape. This is actually 5 comma 5. I don't remember if it's a tuple or a list. I think it's a
It's
tuple.
tuple, I think.
Tuple, okay. Yeah. Okay. Yeah, so this is the simple solution. It's a recursive solution. Then you will simply return S. Right? But this, what is the complexity of this solution? It is kind
D
of,
raised to n.
yeah, exponential. Yeah, there will be some, it may be little less than n, because then when you hit these boundaries, then those branches will not expand further. But okay, of the order of n, or 2 to the power n, or 3 to the power n, yeah, here. Okay, can you make it more efficient by using dynamic programming? Can you make it more efficient by using dynamic programming?
We can start from left, and sequentially we can store the score of each ij, and we
Yes.
can move forward.
Yes, exactly. So you will make a function called, let's say, you will make a new array called score, and you will use it to. You will make a function, an array called s, which will be have, so there is an a already defined, right? Which has a shape same as a. To initialize s, you can either say np dot array a dot shape, or what I do is I will, instead of using this, I will just use s is equal to a into 0. Oh, this is actually not array. This is np dot zeros. You're initializing it with some value, maybe zeros or something. Okay. Now you will say s. You can fill up all these values like this. No, it's not required. Okay, you just apply the for loops and then compute it. I think that is simple, right?
Yes, sir, we can try to do that.
Or another solution is, just like you did here, you created a map, right? Where was it? You create this map. You can also create the map to the sub-problems, right? You can pass a map along with this. This was way one. This was one method. This was second method. I'm telling another third method, where you say define score I comma j comma that map, right? This map essentially maps I comma j, or it has to be tuple I comma j, to a score, right? You will simply check if I comma j, if I comma j in map, then you return map I comma j, right? Or else you compute the further thing, right? So both these, or all three of these methods are correct, but this one is very complex, time complexity is very large, memory complexity is large. This method is very efficient, and this method is, both are same kind of efficiency wise, both are same. But okay, this will again be recursive, but here it is recursive, but it stores the values for quick reference. This one is non-recursive. Right? This is recursive. This is recursive. This one is non-recursive.
Sir, can you tell the method 2 once again?
Method 2.
Yes, sir.
Let's apply a for loop here. For, let's say, instead of I comma j, I can call it as something I1 comma j1 something. For I1 in range a dot shape 0. For j1 in range a dot shape 1. Right? Then you compute these values, simply just use this form to compute s progressively. Right? You can say s I comma j is basically ai comma j. Oh, actually, you may not need to go to the end of this. You may stop at I comma j only. Right? Why to go to the end? Oh, but the problem is, okay, you have to go layer by layer. Yeah, but still it's fine. For I1 in range I plus 1, J1 in range J plus 1. That should be fine. Why to go to the end? Okay?
Yes, sir.
Yeah. And then you can simply say here, write down this formula, and then that's it.
Okay, sir.
Okay, I think so we can stop here. If you have any questions, feel free to ask.
Sir, about the assignment.
Okay.
So,
I will stop the recording in just a moment.